The statistical physics is the point, or it's a go-to branch of physics for us to study the quantum systems at quantum level, and how are these quantum systems when they interact, how are they evolve. So all those things are actually with the temperature they're actually interacting. Okay, so with the temperature they're interacting. So what happens? Of the way they're interacting, the way they're evolving, not only with the temperature, the way the energy of the systems are changing, all those things we can only study using quantum statistical physics. Okay, so here if we have seen, I'll start with studying the system at a tiny level, or I can choose a collection of many systems, make a macroscopic and study them at a large classical level. Okay, now I don't want to study at a classical level, I want to study at a quantum level, because my systems are so tiny, okay, so fragile. So when I say I'm not dealing with a single system, even at a macroscopic level, I'll take a collection of several qubits together. Okay. When I take a several qubits together, they may be having a strong interaction, they may be having a weak interaction. Okay, when they're having a strong interaction, there will be a very tedious job for me to do the calculation and see interactions between them and how they evolve. Okay, but when they're weakly interacting, it becomes easy for me. In that way, I just approximate individual systems are behaving as if they are not bothered about the error surrounding things. Okay, so in that case, the life becomes very easy for me. Okay, even if I go quantum mechanically, a very tiny level, okay, I can bring in something called quantumness, something called duality, something called wave nature of the system. Using the wave nature of the system, I can represent the system using the wave function psi. Okay, using the wave function, I can represent the system, and from there on, I can specify the system behavior in terms of the wave function. How that wave function changes, okay, so I'll just put the system to exposure to the surrounding in terms of the system surrounding with the potential. Well, it's called a potential system in which it is existing. It is just like you take a small ball, a curved ball, okay, take a ball and put a marble inside, and just to give a small twist, the marble goes back and forth like an oscillating. It is just doing a marble inside a, a ball, a curved ball. So marble is making an oscillation. So even in the same way, if I take a small quantum particle, put inside a quantum well, just like a ball here, that is the potential of that ball is just like a potential of the particle inside a box. Okay, so that is actually captured in terms of u. Now the system is allowed to move here and there spatially, so that is actually comes out as kinetic energy. Right, yesterday we did discuss how do we convert the kinetic energy in terms of the spatial second order derivatives. On the right hand side, you see the energy is converted into the energy operator, which is like a time derivative. So altogether, this entire Schrodinger equation would dictate or give a dimension, like dynamics of the quantum state, how it is varying in time, or a quantum system varying in time. So you can see the quantum system in future connected to quantum system in the past using a unitary operator. We have seen the unitary gates, right? So those unitary operator actually use in fact, that u and this u is slightly different. This potential is different. Let me have a potential with the u dashes. Okay, so unitary function. Okay, unitary function actually captures the information of the surrounding in terms of the Hamiltonian. Okay, let's say somebody is not specifically specified what is the u potential. In that case, you can just simply give the Hamiltonian in terms of some matrix, and Hamiltonian matrix giving us some unitary gate. that unitary gate putting on some effect on the old quantum state, giving us the new quantum state. Okay, right? So this is what we discussed yesterday. Now, for the time being, if I just take an exact example of a quantum systems and its descriptions. Okay, so quantum system, for example, for me, an electron revolving around the nucleus, it's a potential quantum state for me, because that electron may exist in that particular orbit and it may go to some other orbit. Okay, so there is a quantum superposition state for me. If I send a superposition, like some kind of a energy pulse of photons, that put the electron in superposition of level 0 and level 1. Okay, now that is superposition for you. And superposition can also be exist in other way around. What is that? It can move in a clockwise direction, electron, or it may can move in an anti-clockwise direction. Because of the rotation, angular spin would be either up spin or a down spin. That is what I have. The spin of the electron at a given point, it is again ambiguous. It is not going to be fixed. Okay. So what I will say, right? What I will say, the quantum spin is also in multiple forms. It can have plus half or a minus half. I'm sorry, right? It can have plus half or a minus half. Okay, so I can put that captured inside my quantum wave function along with the position operators, momentum operators, and I'll have a spin operators, just like I was showing here. Okay, so electron inside an atom, if I take it as a single entity, not interacting with any surroundings, what I will do, I use a quantum harmonic oscillator. It is just like a simple pendulum. Only thing is, it's so tiny, it is so fragile, it might get affected by the surrounding. I would treat that it is only have its own domain. It is not going anywhere beyond. It is not interacting with any surrounding. In that case, I can solve the Schrodinger equation explicitly by taking potential into the consideration, and I can show it exists in various energy levels or the orbits starting from n equal to 0, n equal to 1, n equal to 2. Okay, right? So that is one way of seeing the things. Here, n is actually called a principal quantum number. So which tells me where the electron is located, whether it's located close to the atom as a nucleus or away from the nucleus. Okay, right? So quantum particle confined in a box, where box doesn't have any potential. It's like zero potential. In that case, U potential, whatever I was having earlier, you can make it 0, and you can just solve the differential equation of second order with E as a number, not as an operator. Okay, energy number. So in that way, you can find what is the corresponding energies with which this the quantum particle inside a zero potential could exist in multiple energy levels. You see, multiple energies depending on depending on the principal quantum number. Here in this case, corresponding to each dimension x, y, and z, I'll have a different quantum numbers, nx, ny, and nz. And the wave function is a sinusoidal wave function. You see, it's a nice sinusoidal wave. You see, okay. Now that is a quantum mechanics for you. All right, in a classical way, what we do, we represent a system moving in, like say, two-dimensional surface. We'll specify its location x and y. Similarly, there is something called, I can specify a phase space for a particle or a system which is moving in that phase space. Here in this case, just like x dimension and y dimension, I'll have position dimension and I have momentum dimension. Okay, so in the position and momentum dimension, what happens? The particle is moving with particular velocity and particular position, changes at every time. So what I'll do, for a very small infinitesimal change in time, let's say position is acquiring some delta q change, momentum acquires some delta p change. So what I will do, new position I can connect to old position by slightly adding or subtracting these small changes in position and momentum. So basically what I am doing, I'm dividing entire phase space into small kind of a pixels, where each pixel would specify the location or the state of the system from the old form to the new pixel means new form. Okay, remember how small I can go, the size of this pixel is actually dictated by how infinitable the small change in q, small change in qp we can have. Okay, right? So, right? So, classically I can do anything because there is no limitation. But when it comes to quantum mechanically, Heisenberg uncertainty principle would always come into the play. It will say you can't have a precise measurement in position, precise measurement in time, sorry, in momentum, more than the Planck's constant value. Sorry, less than Planck's constant value. So you can always have a limitation. So this product would always go above the Planck's constant value, which means the in the case of quantum mechanics, the pixel size, the unit size for the accuracy cannot be less than the Planck's constant. It is more than the Planck's constant. Okay, so that is what we studied yesterday or discussed yesterday, and today we'll go to something called a collection of all those systems. Like collection is called ensemble of those all these quantum systems together. Now probably they may have interaction, they may have weak interaction. Okay, right? Now, here I have something called quantum ensemble or statistical ensemble. So, we can, as we discussed, we can have complete description of the collection of all of them, giving a position for each one, giving a momentum for each one, giving a, let's say, spin for each one, and specifying in terms of their wave function. That is possible quantum mechanically. Classical mechanically, what we simply do, we just know the position and know the momentum. That is enough to find what is the system in later times. Okay, but here we are considering a system with an ensemble of particles. Many particles are there. Such system should be characterized by different macroscopic parameters. For example, pressure and magnetic moment required. Okay, but if I have to specify the magnetic moment, what are the magnetic moment overall value it would be? So overall magnetic moment of all those collection of systems would range between some specific magnetic moment value to some small change in the magnetic moment, because I can't give a precise value, right? I always have some error. So there is a range between delta m to delta m plus sorry, mu m to mu m plus some delta m range we can specify. Okay, so there is a possibility of the system would exist some delta m, okay, sorry, mu m plus some small tiny range. Okay, so there are various possible states accessible for this systems, because we'll come to that as we go through. Let's say, right, for example, let's say I'll take a 10 students. Okay, among the 10 students, different students is having a different capability, right? For example, some of them are very strong, some of them is very weak. Together their strength, if I have to measure, I would say give or take they are capable of doing some certain task. Okay, plus or minus some error I'll give. So likewise, a quantum systems, when I take together, their overall quantum magnetic moment would be specified between certain range values, not exact values. Now, that range values means I am not specific. What are the range values? I would go from some magnetic moment values, say from fixed units to certain fixed units range. Okay, so within this range, all the systems would rearrange and have various possible accessible states. That is what I mean. So when I take a system, like some of them is arranged in a certain fashion, some of them is arranged in a different fashion, will lead to different possible overall magnetic moment. So just to understand that, we have an example here. Okay, for example, if the system is taken, if it has a magnetic moment, okay, it magnetic moment is represented by some magnetic spin. Okay, right? If it is isolated, Okay, right? As per the basic postulates of statistical mechanics, isolated system in equilibrium means it is equally likely to accessible all the possible states of that particular energy or that particular magnetic moment. Okay, right? If it is isolated, if it is not isolated, which means it might get interacted, change its states. Okay, right? So just for a one system, if we see here, if it is, has a magnetic moment mu and its spin magnetic momentum would be half, and it have a magnetic moment minus mu, so its spin magnetic momentum would be minus half. Okay, now if we expose this magnetic moment for the external magnetic field, let's say environment, in that case, if there is an external magnetic field is having some h value, I can always multiply that magnetic moment of that particular individual system with the h value, and has to put a negative sign because it is always imposes the opposes the external magnetic field. Okay, so I'll have any system with a spin half positive magnetic moment will have an energy of minus mu h. Okay, if the spin minus of magnetic momentum is there with the particle, and it will have an energy of mu h when it is exposed to the external magnetic field h. Okay, so the total, if the total energy is just a mu h, then the accessible states would be few of many possibilities. What are the few of many possibilities? It could be plus half and minus half. Okay, so just now let's take a collection of few systems. Now this table will explain what are the various accessible states for a given combination of a system. Okay, so carefully look at here. I would quickly describe this. Let's say I have a three spin particles. Okay, right? So let's, in a way, like a three qubits, spin qubits, right? So here system is allowed to have 8 possible states with this spin qubits, three spin qubits. What are those 8? You see, all of them have positive spins. One of them have a negative spin. Which one? We don't know. The last one or the mid one or the left extreme one can have a negative spin. Okay, and there is another possibility, two of them have a negative spin. Okay, which two of them? The last right extreme or the left and right extreme, and all the way left extreme, two of them, okay, they can have negative spins. And another possibility is all three of them have a negative spin or a spin down. Okay, so this, when I take a three systems, when I take a three systems, three spins particles in a system, these are the 8 possible combinations of their arrangement. Okay. Now, as we saw, what is the total magnetic moment? See, all of them contributing equally in a positive side. We have a 3 magnetic moment values, 3 into mu values, magnetic moment. Okay. If one of them is negative, that will nullify the other one. Will have a resultant magnetic moment mu in the next 3 cases. Okay, if I have two particles of negative magnetic moment, means one of them cancels the other one, so I left with minus mu as a overall magnetic moment. Okay, so how many of that kinds are there? 3 of them are. Now the another extreme situation is all of them is arranged in a negative spin manner, so their magnetic momentum would be minus 3 mu. Okay, so if these three particle system, spin particle system, if it is exposed to external magnetic field, you can calculate what is the corresponding total energy. Okay, interestingly, if you see, for example, let's say take the situation where, let's say I'll put the index values for each combination. Let's say R is equal to 1, all of them in positive spin, R equal to 2, and 3 and 4 would correspond to one of them is having a negative spin, other two having a positive spin. In that case, if you see, the overall total energy is minus mu h, overall magnetic moment is mu. Okay, so the overall state is having the energy same, but the rearrangement can be different. So there are three possible scenarios, three possible scenarios. Okay, right? Arrangement, just rearrangement in between them would lead us to two different state arrangement, but overall total magnetic moment, overall total energy is same, but rearrangement may be different. So this is what the accessible states for a quantum system arrangement, accessible states. This is what I was meaning earlier. Okay, so if I have a system, three particle system to exist with total energy of magnetic energy of minus mu h and total magnetic moment of mu, if I allow the system to have these two values, but if I allow the system that can arrange in various manner, how it can arrange in three arrangements. Okay, for example, if I want to have a total magnetic moment of mu h, then again here system can have rearrangement in three possible ways. Okay, so when I say a system of total magnetic moment of mu h, which means system can arrange in three ways, three accessible states. Okay, by just internally rearranging, they can have three accessible states. Okay, and remember, overall energy is same, overall magnetic moment is same, but the rearrangement is different. So I would give you equal possibility to exist in any one of the possible case. Okay, because overall energy is the one which is going to make a difference, right? Overall magnetic moment is the one which makes a difference. Okay, but internal arrangement is same, or it can arrange like say here positive positive negative, positive negative positive, negative positive positive. So for corresponding to minus mu h total energy, there are three possible ways it can arrange. Okay, now what the thermodynamics law says, okay, what they say, we can see here, if the two systems are in thermal equilibrium with the third system, then they must be in thermal equilibrium with the third system. Sorry, they must be equal in equilibrium with each other. What I mean is, let's say A and B are in equilibrium, B and C are in equilibrium. Okay, which means A and C are in the equilibrium. That is what the zeroth law says as per the macroscopic world. Okay, now why do we need, let's say, keep this aside of microscopic system of spins. Okay, and we'll try to assess in terms of macroscopic thermodynamics come from statistical physics. So number one law is like that. Okay, fine, very good. And number two law is, sorry, number zeroth law is like that. And the first law says, if there is a macroscopic system, is collection of many systems, if they're in equilibrium characterized by a quantity, internal energy, okay, so if it is isolated, that overall energy is going to remain the same. Okay, if it is perfect isolation, remember. So what I mean, 3 qubits may be perfectly isolated, their internal energy is going to remain constant. Okay, so perfect isolation is like prescribed in this case. Okay, let's say if the system is slightly allowed to interact with the surrounding, here they give a name for the surrounding as a reservoir. Okay, let's say surrounding has some temperature, ambient temperature, the temperature is supplied in terms of heat to the system. In that case, what happens, there is a change in the internal energy of the system. So how it is going to affect in our quantum system of three spin particles, probably the internal energy or total energy of mu h of the three particle system may slightly vary. How much vary depends on how much heat is being supplied. Now, there is a heat supplied, which means there may be rearrangement in the system of spins that is actually represented in terms of some work done macroscopically. In a negative sign shows amount of work done here. Okay, heat supplied, energy is consumed in work done. So how much heat supplied, there is a negative sign of a work done. out of Q, some work done energy is removed, remaining energy is going to add up to the system as some positive quantity. Okay, right? So that is what the first law of macroscopic statistical physics says. Now there is a one more law also is there, and we just try to revise or recollect that. What is that law is? Okay, what is that law is? If a system is in an equilibrium, okay, a macroscopic system in equilibrium which is perfectly isolated, in that case its entropy is not going to change positively. Sorry, it is entropy is not going to decrease, it is always going to increase, or it going to remain the constant. Means disorderness in the system is going to remain constant, or it may increase if it is not isolated. If it is isolated, it is going to remain the same. What I mean is, let's get back to our old system. If it is perfectly isolated, the rearrangement is done in such a way the order will remain the same. What is the order? Let's say here positive, positive, negative, or negative, positive, negative, positive, or negative, positive, positive. So the arrangement is perfect. What is that arrangement perfect? One of the negative guy is sitting either corner or in the middle. Okay. So that orderness would remain constant, or if it is allowed to interact, that may go beyond our control. The orderness may go be positive. So how? Let's say if it is not isolated, in that case, the heat will come in, it may do some work, it may do, by doing that work, it might increase the entropy, disorderness in the system. For example, here in this case, the spin of one of them is flipped to have additional energy. Okay, from minus mu h2 it may go to plus mu h by flipping one of the spin of the system. That is what showed as per the second law in terms of variation in the entropy. Okay, you see now we took a macroscopic systems of three spin particles and we are trying to assess in terms of the thermodynamics macroscopic physics laws. Zeroth law, the first law, and the second law. Okay, right? So here system is undergoing quasi-static infinitesimal process, the change in the process. How? With acquiring a small increment in the entropy, disorderness in the system. That is what the second law we connect and use to understand our quantum mechanical systems. Okay, you see now how statistical physics is helping us to understand the two qubits, the three qubit spin systems to do some quantum processing. How we have to deal with them is done by statistical physics help. Okay, and there is a third law. What it says is, third law of quantum statistical physics says the entropy of the system has the limiting property. What is that is? Let's say I reduce the temperature to very close to absolute zero. Okay, right? In that case, what I can do, I can put the entropy of the system to a constant value, which is going to be independent of all the parameters of the system. Very, very important. Okay, what I mean is, if I reduce the temperature to absolute zero, in that way I can put the system into an order where I am not going to worry about the order change at any level once the temperature is ensured at absolute zero. That is what people are trying to do. They're taking a quantum chip consisting of so many quantum qubits and put inside a cryogenic liquid which is enclosed within a large deep freeze cylinder. In that way, I have no need to bother whether the spin is going to be affected or not. If my temperature is put to millikelvin, okay, so the order is not going to be changed with the delta S going to be zero when I have absolute zero temperature. Okay, so third law also giving us the indication how to have a control over the quantum processing units by reducing the temperature of the quantum processing units to absolute zero. That is why people are doing putting the quantum chips at a millikelvin by using liquid helium, liquid nitrogen, liquid hydrogen, and pouring, and layer by layer they reduce the temperature of this deep freeze cylinder. At the bottom the chip is going to sit. So why millikelvin as of now? There are something called superconductor based qubits, superconductor based qubits. So these are called transmons. Okay, transmons. So this needs that absolute zero or close to millikelvin is fine to have the qubit behavior. Okay, right? So all the four laws, note that they are macroscopic, means they are dealing with the large systems, a collection of microscopic system with no reference to microscopic nature explicitly, but still we can incorporate and understand the system behavior together, like few microscopic systems together, three spin systems together. We can use this all the three or four laws to understand and use for our effect. Okay, right? So here I have microscopic property of a system will be designated by statistical relations or designed by or designated by statistical relation, which is actually Shannon's entropy. S is equal to K, or a Boltzmann constant K, multiplied by log of omega, the capital omega. What is this omega is? It would refer to the possible accessible states as per quantum mechanics, not as per the statistical mechanics, as per quantum mechanics. Okay, so what is this omega stands for? In the previous case, omega stands for the number of accessible states, number of arrangements. Here there are three arrangements. So the omega stands for those three arrangements, three accessible states. Remember that. Okay, we would be using these three accessible states, omega, okay, to represent our entropy of the system. Okay, I will connect the orderness of the system into the accessibility of various possible states of our microscopic qubits. Okay, so right, so this was the about using a statistical physics to deal with the quantum mechanical microscopic systems. So what I will do, I will get into the zone where we will talk about various possible accessible states for a quantum system collection. Okay, so let me go for the next PPT, next lecture. Okay, where is the next lecture? Give me a minute. Okay, so it is called canonical ensemble. Okay, so there is a lot of text is there here. What I will do, I'll use my hand board note to explain slowly. Okay, so that you would follow. Okay, right? So what I'll do, I just will take another 10 to 15 minutes. I will describe what is a canonical ensemble. Okay, and then we'll take a 5 minutes break, and then we'll come back and we'll complete how are we going to deal with a collection of quantum systems as a canonical ensemble. So there is a question here: can we say the qubits uh, with the total same energy have degenerate states? Absolutely right. Your Rajesh Rajeshwari, is it? Yeah, thank you, Sir Rajeshwar Rao, sir. Rajeshwar Rao ji, absolutely right. So three qubits with the same energy rearranging in different fashion. Okay, rearranging different fashion means rearranging in different quantum states having same total energy. Okay, so it's a degenerate states. Degenerate state, degeneracy comes when we are talking in terms of eigenvalues and eigenvectors of a matrix. Same eigenvalue having different eigenstates. Okay, that is a degeneracy there. Similarly here, yes. That is what we meant here. What is the fourth law? The fourth law is, yeah, we just saw that. So when I isolate the system and fix the system temperature to absolute zero, T goes to zero. In that case, I no need to worry about the orderness in the system, because I presume myself orderness in the system, the entropy in the system is going to be a constant. That is what the fourth law says. So that is why, as per the fourth law, people are following actually. They are reducing the temperature of the quantum systems or the qubits to absolute zero, so that they are not going to go out of order, disorderness. They will not go. Okay. Right. Okay. So canonical ensemble. Okay. Let me start my notes so that we will have a better understanding with an explanation. Okay. Canonical ensemble. Right? So the name stands very fancy. Ensemble is a group of system, very simple. Okay, right? So from the statistical physics it comes. Let's say canonical ensemble means I'll fix the overall energy of the system to some value, some range of value. In that way, system is allowed to have various combinations of accessible states. Those accessible states I will deal with canonical ensemble description. Okay, right? So that is what the canonical ensemble is. Now let's consider okay, isolated system A, perfectly isolated, right? So in that case, there are internal rearrangements that may be fixed. Okay, they're not be much fun, because it is an ideal situation. We cannot have ideal situation in any way. Even if you try to pull it to absolute zero, you will not be able to reach that value. Okay, so you will be going close to that. So let's consider isolate system. Okay, in case if it is if if it is reacting with the environment, okay, right, it is interacting with environment, I would say reservoir. Okay, I would say reservoir. Let's say the reservoir I'm representing as A prime. Okay, so the reservoir is a prime. So what is the overall system? The overall system is A plus A plus. Overall system is going to be A plus A prime. Okay. So A prime is there. Now what happens? The system, let's say by nature, it is having a arrangement in such a way, it can have a range of energies. Okay. Right. So, okay, it has a range of energies, which would be the system may have, okay, energies ranging between E to E plus delta E, because by the nature of quantum mechanics or quantum level, even if you are isolated, okay, system is isolated, it could consist a constant energy which would lie between E to E plus delta E. Okay, so internal rearrangement may slightly give a small variation. Okay, now I'm talking about a reservoir. Okay, if the system is interacting with the reservoir, then I have to worry about that also. Okay, so now let's say, right, so I'll have probability of finding the system in any one of the state is equally likely. Okay, earlier we have saw that. Okay, so let's say system is being in a state AR. Okay, what is this R stands for? For example, there the in table which we earlier I was giving a table, right? where R1 stands for all of them in arranged in the same fashion. If R is equal to 1 stands for one of them is misaligned. Okay, so the system is having arrangement like AR with R equal to some fixed value, and the corresponding energy is ER. Okay, so with R equal to some fixed value, let's say R equal to 2, R equal to 3, R equal to 4 case, the R is the index where plus half, plus half, minus half, minus half, plus half is the arrangement. Okay, right? And plus half, minus half in the middle, plus half is the arrangement of three spin systems. Okay, R equal to 2, so R equal to 2 is here, R equal to 3 is here, R equal to 4 is here. Okay, so for those three cases I am talking about, overall energy is actually ER is same. We saw that. Okay, so energy is same. System can either exist in this form or this. It can exist in all the three forms equally likely. So what is the probability of existing in particular R form is 1 if energy of the system exists between ER to E plus some delta E. Okay, if the energy goes anything other than that ER value, I would say this three cases system would not exist. I would say otherwise. Okay, so this is a probability. So probability of existing in all the three accessible states is equally probable. So probability is 1 there. So overall probability, if I want to calculate for all the index values, is going to be 1. Okay, so just to avoid, there is a 1 here, there is a 1 here, so the probability should sum to 1. What I will do, I'll put some constant C, which will take care of that normalization factor. Okay, so what I mean is, let me go on, use this, the previous situation, and explain what I mean. Okay, let me go and go to the table. Okay, here you see 2 R equal to 2, R equal to 3. In all the cases, I have the overall energy is minus mu h, overall magnetic moment is mu. Okay, right? So if I ask out of the 8 possible arrangements for this 3 spin system, what is the system to have an energy of minus mu h and magnetic moment mu? That would be the probability wise 3 out of 8. Okay, so 3 out of 8 is the individual probability for R equal to 2 and 3 and 4. Okay, so 3 out of 8 is a 3 by 8 is the probability, and the remaining cases is there, and there also comes out with their individual probability. If I sum all the probability, it should sum to 1. So that is what I have, summation over PRs is giving you 1. So to take care of it, I'll have a normalization C here. Okay, for the time being, you can just assume that this is the probability of 3 cases which are equally likely given here. Okay, very good. Now, so what is the overall energy? The total energy we have to worry about. Okay, so overall system, let's say now overall system. Overall system is system plus environment. So which is going to say, I'll say overall. And similarly, the overall system energy is, okay, the system plus environment energy. Okay, and what is the system energy? Let's say ER. The system energy is ER. Okay, overall energy is E of O. Let me write in terms of the environment energy, which is going to be overall energy minus ER. Now you see reservoir is a very big quantity. Surrounding is so big, the entity is so small. So reservoir energy is okay is not going to change much with the system taking energy from the reservoir. Okay, right? So, and moreover, reservoir can have arrangement in such a way, okay, it can exist with multiple arrangements. Okay, so that will be very vast, by the way, remember. So just like particles arranging themselves in a different order, reservoir also arrange in a different order, which would be definitely going to be a big number. How much number? Just now we saw arrangement for the three qubit system is just a three accessible states. When I want to write for a reservoir, which is going to be the number of accessible states, number of accessible states for the reservoir. Okay, it's going to be a huge number because the energy of the reservoir is just overall energy of the system, my overall energy reservoir plus system minus system energy. Okay, if say this is a big number. Now, if I ask, what is the probability of the system to exist in a state R? Obviously, it is going to be depending on this accessible states of even the reservoir. Okay, even the reservoir. Number of accessible states for the reservoir. Number of accessible states of the reservoir. Okay, I'm just trying to derive what is the possibility. Now, if I want to explicitly write down what is the PR dependence, you can say there is some constant C prime, which I don't know right now. So just omega prime E of 0 minus E of R. Okay, right? So some implications here. Let me bring it for you. A is very small, or you can say very, very small. Means the energy of the A is or R is much smaller than overall system. Okay, which means omega prime of E of O minus E of O, okay, is a very large, varying function. Very large varying, and means it is fluctuating like anything, rapidly fluctuating. Okay, because it is not minding about the system. Okay, so which means it is very rapidly varying or largely varying. So just to put into the context of our understanding, to have this making it slowly varying, largely varying, slowly varying, I want to make slowly varying for the mathematics, slowly varying for the sake of understanding. What I'll do, I'll take a log of or natural log of this omega. Okay. Once you do that, what happens? It is slowly varying function. Log of large number is very small number, right? Okay. Now, if you see carefully, this function, which is okay, it is like a function of some x plus or minus some quantity a. Okay, x is equal to some value a. About x is equal to a, this function is fluctuating. So what I'll do, I can do a Taylor expansion. Taylor's expansion. Because I want to understand, okay, I want to understand how system AR behaves. Okay, right? By any means behaves when it achieves or obtains the energy E is equal to overall energy. That is extreme, but still it is possible. It can take full energy, like giving from the system. So in that case, I want to find them. Okay, AR is equal to, sorry, overall energy is equal to the system, or you can say for the comfortability, let's say the reservoir energy is not going to be any variation at all. Okay, so we have here reservoir energy, okay, and we have energy of the overall system. Okay, so what I'm doing, I will be expanding in a Taylor's expansion log of omega prime E of 0 minus E of r is equal to log of, okay, omega prime, okay, E of 0 minus, okay, derivative of log of omega prime with respect to E prime. And what value? E prime taking a E of 0, right? Multiplied by ER. So this is what my variable, ER is my variable. With respect, sorry, E prime is my variable. This is just a constant. So that is what the Taylor expansion of this function would have. Okay. So my higher order terms will be there. Added terms. Now, if you carefully look at this expression, the derivative of, okay, derivative of log omega prime with respect to E prime, if you look at it, at E prime is equal to E of 0, which looks like 1 over Boltzmann constant. Okay, so which is actually written as a beta. Okay, where 1 over k beta. So what I will do, I'll just introduce dimensionality wise, it's some Boltzmann constant. Okay, so I'll introduce that log of omega prime E of 0 minus E of r is equal to log of omega prime E of 0, okay, E of 0 exponential, sorry, E of 0, right? Yeah, minus beta of E of 1. Okay. Now I have a logs on two terms, no terms on the log. You take a exponential of this entire terms, entire equation. So if I do that, I'll have omega prime E of 0 minus E of r is equal to omega prime E of r exponential minus beta ER. Okay, right? Now you see there is a number of accessible states of omega prime with the total energy independent of r, the index rearrangement. Okay, so what I will do now, since that is the situation, I will write the overall probability which I was earlier I wrote. Na? So where is that? This is the overall probability. Now I know what is this expression in terms of the Taylor expansion result. I'll put that into that. I'll get PR is equal to, okay, some C prime, okay, right, omega prime E of 0 minus E of r. Now if you substitute this here, okay, what I will get is C prime omega prime E of 0 E of 0 exponential minus beta ER. Okay, what I'll do, I'll capture this both of them into new constant C exponential beta ER. Okay, now by the way, I don't know what is C. To find C, I'll use the condition sum of PRs is equal to 1, which implies the overall probability PR is equal to exponential minus beta ER divided by summation over EBER. So this is a probability with which any given system can exist is actually obtained from the accessible states. Okay. So this is called a canonical distribution. Canonical distribution. Okay. Right. So where the denominator, whatever you see, is actually something called a partition function. We'll come to that in the later part. So right now, what we did, let me conclude. We took a quantum system, collection of many individual quantum systems, maybe interacting. Okay, it might have affected the environment. How environment gets some multiple possible states. From there, I derived whatever is the possible states for my system with 3 spin qubits or any number of spin qubits. What is the distribution of rearrangement or the probability of any given rearrangement we just got in terms of some expression involving energy of the each rearrangement. So in the denominator we have various rearrangements summed together. The numerator have only one of the specific case. Okay, right? So we'll just take a quick break here and we'll come back and just to see what are the implications of this probability canonical distribution is going to have for our quantum computing. Okay. Break. Tell me, Rishi. Some doubts or problems. I think someone will. Oh yeah. We'll have a presentation soon. Yes, everyone, I think we can start. Okay. Yeah, please remember one thing. Most important thing, a take home from the discussion so far is we need to find out what is the probability distribution of a given collection of quantum systems. So PR is going to be very, very important, just like our regular PR. And the probability of given arrangement with accessible states is going to be very, very important. Okay. So just for understanding what we can do, we can take a simple example. Okay. So before going to a simple example, if you carefully study this expression, okay, this expression, if you carefully study, right? Okay. So in the PR, there is a omega of A, there is exponential of B of E, right? So usually this is a very large, depending on if I have a large number of systems, the number of accessible states will be large, exponentially large. You see, in quantum system, if I have two qubits, they can be arranged in 0, 0, 0, 1, 1, 0, 1, 1. Okay, two qubit system. If I have three qubit system, where I can have arrangements like 0, 0, 0, 0, 0, 1, 1, 0, 0, 0, 1, 0, 1, 1, 0, 1, 0, 1, 0, 1, 1, and the last one is 1, 1. So three qubits can lead to arrangements of 8 possible states. Okay, right? If 4 qubits, 16, 5 qubits, 32. Okay, so on, exponentially increasing. So this function accessible states is exponentially increasing. Okay, are rapidly increasing. But exponential beta E of ER is exponentially decreasing. Exponentially decreasing. Okay. And what I see from here, PR is going to be, if I plot energy versus PR, it is going to be just a peak. Because increasing function is there, decreasing function is there, they are going to meet at some point and there will be result E is equal to ER case, it is going to peak. So that is what we have. Now, if the number of states, okay, is large, we'll have a peak of certain height, okay, right? So large A, larger the A, sharper is the peak. Okay. So if the A is large, then PR will have sharper, will be sharp. Okay. So that is what this canonical ensemble distribution of system will be understood in that way. Okay. Now, so we just took three qubit system. Okay, let's understand a paramagnetism using this canonical ensemble. Okay, so just for the case quicker, I have like 45 minutes or so. Let me use my hand notes as it is. So we discussed, yeah. So paramagnetic system I want to discuss. Okay. So paramagnetic system is what? Consisting of atoms of spin half, okay, with the intrinsic magnetic moment of some mu, okay, some spin half, right, spin half, and intrinsic magnetic moment of mu. That is what magnetic paramagnetic materials are actually made with. Okay, right? Now if it is exposed to some external magnetic field H, okay, each spin would either gets aligned positively or anti-parallel negatively for the applied field, right? What I mean is, if there is a spin half system, electron is revolving about itself. Okay, so let's say it has a spinner. When there is external magnetic field is there, B, whether it is arranged as per the external magnetic field direction or not is represented by arrangement of parallel, anti-parallel or parallel, total magnetic energy. Okay, so if the atom aligns, the electron arrays parallel to the applied magnetic field, I will associate an energy E plus with a minus mu H. This we did already. Okay, if it arranged the opposite way, so overall energy is mu into applied magnetic field energy. So usually people use H for magnetic field representation. So we will have magnetic field H. Okay, so H is used for so many cases. Hadamard matrix. H is used for Hamiltonian. Okay, so remember that. Now I have this. Okay, now as per my canonical distribution, can I bring whatever discussion we have did so far and put it here? Okay, so the probability of atom to exist in plus state would be what? Some constant exponential of beta into energy of plus state. Okay, so what is constancy? We'll worry about later. Okay, so from the canonical distribution, I just express that. Okay, so E plus is explicitly mu of H. You just substitute. What is the chance of various possible arrangements with each of that arrangement having energy E minus? So you can get a probability of P minus. Okay, so explicitly convert the E of minus in terms of magnetic moment and applied magnetic field, you would get some expression. Okay, right? Very good. Now let's go and find out what is the mean magnetic moment of this system when it is arrangement, possible arrangement in positive way, possible arrangement in negative way. So it is actually fluctuating continuously like a superposition. So in that case, I'll have some mean magnetic moment. What is that mean magnetic moment is? With a P plus probability, it exists with magnetic moment mu. With a P minus probability, it exists with a minus magnetic moment. So what is the total probability? It is just a P plus and P minus. Okay, explicitly you substitute whatever we derive into this expression and you get what is the mean magnetic moment is. In fact, there are exponentials involved without any complex number, so it will become hyperbolic, tan hyperbolic function. Okay, you can take a mu common and write mean magnetic moment as tan hyperbolic mu h divided by kt, where B is connoted in terms of K into T, Boltzmann constant multiplied by time in an inverse fashion. Okay, so let's say mu h by Kt is a ratio of magnetic energy to the thermal energy. Boltzmann constant multiplied by T is actually thermal energy. So it's like magnetic energy to thermal energy ratio. So exponent E of y, exponential of y, where y is always less than 1. You know why? Thermal energy is always going to be a large quantity when it compares to magnetic energy. Okay, so which means I can write exponential of y as okay, remember there is an equality. Okay, 1 plus y plus so on. Okay, so exponential of positive y is there is a positive y here. Exponential of minus y, there is a minus sign comes in the expansion. Okay, so if you use this, I'm sorry, I have to put a division. Okay, if I use this conversion I'll have overall tan hyperbolic is just simply equal to y. Okay, so mean magnetic moment is simply y multiplied by the actual magnetic moment. What is y? Y is this quantity. Okay, so now explicitly if you write down, magnetic momentum is equal to mean magnetic momentum is equal to magnetic momentum square, okay, multiplied by magnetic field, applied magnetic field, divided by Boltzmann constant. If y in any case, let's say y is larger, okay, the other way around, what is that? Magnetic energy is much larger than thermal energy coming from the surrounding. Okay, so I have isolated perfectly, and applied magnetic field is larger, and energy coming from surrounding is very small. In that case, what happens? E of y is much larger than E of minus y. So tan hyperbolic simply becomes 1. So mean magnetic momentum simply becomes mu. So perfect magnetic momentum means system is isolated, perfectly isolated. So this internal magnetic momentum is not going to change. If it is allowed to interact, in that case, I'll have some magnetic momentum value as per this. Okay, so which is actually correlating the reality. Okay, our canonical distribution which we derived is correlating. It is actually making sense. The probability distribution which we derived. Okay, this one making sense when I take a paramagnetic movement material study. Okay, right? So very good. So the mean magnetic momentum of entire system, if I want to write, so let's say there is a n naught number of atoms per volume, okay, so which is n naught multiplied by the individual mean value of internal magnetic moment. So I'll get to overall mean magnetization of the entire system. Okay, so if you want, you can plot where m naught versus the ratio of energy, magnetic energy versus thermal energy, that is y. So which is increasing quantity and stabilizes later. Okay, so this is the characteristics of paramagnetic material. Paramagnetic material, which means our canonical distribution is actually giving the characteristics of magnetic material. Okay, applied magnetic field versus magnetization, if you find it is increasing like this and stabilizes later. Okay, very good. Now we are through. Now let's go a little bit further. So calculation of mean values using canonical distribution is actually like described or coined as a name of partition function. So what is this partition function is? I'm dividing various possibilities into partitions and then expressing that in terms of mathematical function. That is why it is called a partition function. Okay, right? So if the system is distributed according to the probability distribution, okay, like this, where explicitly C I got, it's a summation of various combinations. The calculation of mean energy of the system would be using partitions, using probability distribution, you can calculate just like we did in the previous case. How? We just take ER multiplying inside the energy, sorry, inside the expansion. Okay, so what I mean by this, let's use our hand notes to understand what is being done in finding a mean. Okay, for example, let's say I have 10 students. Exam mean 10 students. Okay, so student 1 is, let's say, 5 feet, student 2 is 5.5, student 3 is 5.2, so on. Let's say student 10 is like 5.6. Now what is the average height? Average height is 5 plus 5.5 plus, so on, 5.6 divided by 10. Okay, this is how I find the average height. Okay, if I know the distribution of the height among the students, let's say what is the distribution? Let's say PR is some exponential minus beta, not a beta. Let's say in this particular case, some okay, height of each student divided by sum of minus ER. Okay, so in that case, what is the mean height? Mean height, I will find it as, okay, summation over all possible PRs multiplied by height of each person. Okay, so what is this quantity? This quantity is this, right? And divided by overall number of students, that is PR, by the way. Okay, right? So from here, we can find the mean energy of the system. Knowing the distribution, we can find the mean energy. Okay, so let me remove this. Okay, right? Same strategy you can use for any parameter mean value. Okay, so explicitly, if I want to find, okay, so one can do a simple trick to find what is this E prime. What is that is, if you carefully observe this quantity, you carefully observe, in the denominator I have just a summation, in the numerator I have summation along with PR. What I will do now, consider this numerator. What is this? Which is equivalent to, if I am having a derivative of the entire thing with respect to beta with a minus sign. If I have it, okay, let me do that. Okay, so I have mean energy is equal to summation over ER, okay, exponential minus beta ER divided by summation over exponential beta ER. This quantity I want to find. We need to find. Okay, how do I find? Let's consider summation over eta BER. Okay, I'm sorry, ER also. You take a derivative with respect to beta, this quantity, okay, without that. Okay, now derivative can be sent inside because the summation over is with respect to R, not with respect to beta. So I'll have derivative inside exponential minus beta ER, which is minus beta, sorry, minus ER exponential minus beta ER. So they take this minus outside, minus summation over ER exponential minus beta ER. Okay. So now if you carefully see, this is the quantity existing in the numerator. So I can write E mean value as minus of derivative of summation of exponential beta ER. You will see why I have done this trick. In the denominator, let's leave it as it is. Exponential minus beta ER. Okay. Now, let's call some summation over R E as beta ER as some z, some variable. Okay. Now, if I call that A, mean energy is minus derivative of z divided by z. Okay. Again, I'll play a trick. What is the trick? You just take a log of some z. Okay. Differentiate that log of z with beta. But I'll get 1 over z log, sorry, 1 over z log z. No, not z. No log. Dou z by dou beta that I'll have. Now, this is a quantity which is here, which means the average energy is equal to minus of derivative of log of z. Okay, you see now how things are becoming much simpler when I introduce this kind of a partition, this kind of a trick. Okay, fine. Now you just keep E average energy in terms derivative of log of z. Okay. Now only thing, if I know z, I can find average energy. Okay, right? So then let's say there is a deviation from the energy when I'm calculating energy of the system. So I make a calculation. Let's say, for example, heights of each person I'm just trying to measure. So from the each person measurement, there is a variation from the average. So the deviation from the average is usually equal to measured value from the mean. That is the deviation. If I want to find the variance, so what I'll have this. So which is E minus E bar whole square. Okay. So by the way, what is this quantity? This deviation is, you simply derivate once again, which is simply log z. Okay, right? So the deviation is nothing but deviation with respect to beta. So I'll get a deviation square just by taking partition function, log of partition function, the square. Okay. By the way, you can still further find the power of the partition function z using other expression, other techniques. Okay, let me go through that. So this is the power of partition function. Here you have. Okay. Let's say all the important physical quantities could be expressed in terms of partition function z. Okay. Consider, let's say z is a function of some variable x, some variable, some b. Okay. Where x is what? Inverse of temperature. Okay. Small change in z would be represented by what? Variation with respect to x, small change in log z. Variation with respect to beta, small change in log z. Okay. So this is a partial derivative for you. Partial derivative. Okay. By the way, change in energy of the system due to x change would be simply ER derivative with respect to x multiplied by some change in dx, which is what? Which is simply force into displacement, which is just like a work done. Okay. Since we are losing the energy because of the work done, so there is a minus sign coming in. Okay. So what I'll do, I can replace the work done wherever we will come to that. Okay. So by the way, how much work done on all the possible qubits? Okay, there are so many qubits. What is the, in each qubit we'll do some work. So there's so much of work is done. What is the average work done in on overall in each qubit is simply just like average energy we are calculating, right? Similarly, you can find by substituting what is the actual single qubit energy work done. You just put it and then take a partition function and the probability distribution, and you can even calculate what is the average work done on each qubit. Okay, right? So I have just algebra for you here. So if you can just follow through later, but what is the implication, we'll just see. Okay. So the derivative of log of z is expressed in terms of variation in average energy and internal energy mean. Okay, so this is a variation in beta. There's a small change in beta parameter. Okay, small change in dx actually comes into the energy. Okay, right? Now, whatever is the right side quantity is there, you just send it to the left side. This quantity log z plus e and b delta b. So delta I can send, d I can send out. It becomes a quantity, some quantity. On the right, I'll have, okay, beta into dw mean. Okay, so there is a small addition increment in the energy is taking place. Okay, how did I do this? I use a variation in energy and the beta expressed as two derivatives. Okay, so those two derivatives I just substituted here. So with that, I'll have one more term. So basically, this quantity is actually heat absorbed by the system. Amount of internal energy given, out of amount of internal energy given, some part of his work is done. So that will be together the total heat energy supply. Okay. On the left hand side, whatever is the quantity is there, it's actually entropy. On the right hand side is just a variation in the internal heat energy, dq. Okay, sorry. So yeah, ds is equal to dq, right? So there is a beta missing, I think. Yeah, beta is missing, so I should have a beta. Okay, so in term the beta, actually I had put it as denominator t. Okay, k is missing, maybe I should have a k, right? So if that k is right, if that k is integrated, so I'll have this. So the entropy in the system is k into log of z plus beta into energy. Okay, so this is a total entropy of the system obtained from the partial canonical distribution or the partition function. Okay, so likewise you can do a lot of calculations. So it's a part of part of statistical physics. We are not going into the details. Okay, right? So I'll just stop at this point. It is too much mathematics. If there is any questions, I will take the questions in next 10 minutes. Any questions? How many more? I think I have to cover equipartition theorem. Okay, just to see what are the topics I would be covering. Okay, right. Yeah. If you see, introduction to the statistical physics we did yesterday, and laws of thermodynamics, starting from first law of thermodynamics and second law of thermodynamics also we did today. Okay, right? And we discussed a partition function and probability distribution and canonical distribution we discussed. Okay, and tomorrow we will go for something called thermal equilibrium and Gibbs principle. Okay, right? So, yeah, there are questions coming up here. Let me see the questions. I have a small question from Dr. Manohar. In quantum computing, takes more energy for computing when compared to today computer. Oh, okay. Let me clarify you, Dr. Manohar. It is other way around. Okay. The amount of energy required for quantum computing is much smaller than existing classical computers. Okay. If you want, I can show you with one of the slides. Okay. Wait a minute. 1 minute. Can show you that. So let me present from a different system. Share. Okay. Okay. So I'm sharing some other system. Okay. So let me show a slide to answer your question. Okay. There is a 1 minute quantum computer. Okay. 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 I have a slide. I just want to show you that slide. Yeah. Yeah. Let me show you this slide. Okay. You see here. Okay. So Google has in 2019, okay, they showed something called Google supremacy with 53 qubit chip. Okay. 53 qubit chip, they showed this. Now, what they showed that there is a task which requires about 10,000 years of time to execute on a powerful supercomputer. The same thing, we did it in 200 seconds. That is what their claim is. Okay, fine. Now, let's go to the next, energy efficiency. Okay, right now, the compared to the power consumed by that summit large computer, supercomputer, IBM computer or any supercomputer which required to execute some task, same task like this, okay, by quantum computer. This is a blue force quantum computer, blue force cryogenic setup. Inside that there is a quantum chip. This is basically a quantum computer. Okay, you see amount of wattage of power consumed. 26 kilowatt is consumed by this quantum computer, and 15,000 kilowatts power is consumed by the supercomputer. Okay, right? This is a comparison of energy consumption. Okay, so probably for cryogenic cooling and all, there may be energy consumption, but not at this level. You see, the entire data center has to be cooled, and each processor, each GPU consumes a lot of power. But here there is no thing like that. Okay, so this is the numbers actually taken from the reliable sources. I'm projecting. I'm not just projecting from my own head. This is the numbers. Okay, right? So yeah, this is what our quantum computer from QPI in India. This is the first computer assembled or created or made in India with like arranging uh, chip taken from Netherlands and cooling setup from Blue Force. This is from QPI computer, QPI Bangalore. Okay, this is just a quantum computer. You see, okay, how much amount of power required? About 20 kilowatts. For a supercomputer, 15,000 kilowatts. Okay, right? So this is what I meant. Okay, right. So let's see another question. Okay, I hope I answered your question. Just a minute. Okay, my mobile. Okay, it's stuck. Okay, my laptop got stuck. So let's see the questions. Okay, 1 minute. Vacancy, yeah. Okay, can you hear me?
Yes, sir.
Thank you. Okay, can we measure? There is a question by Satish G. Can we measure partition function of qubits? If so, is it possible to calculate the distribution of qubits and their minimum energy states in quantum computing? A very, very good question, Satish Ji. It's a partition function. It's not like a measurement. We can derive, okay, right? From the probability distribution, we can derive the partition function. Having known the partition function inside a probability distribution, we can calculate any mean energy or anything. Okay. A minimum energy, of course, we can find out. Okay, not using this method, probably a different method. Okay. Any more questions? Okay, I think my laptop got stuck.
Yes, sir. Shall I read the next question?
Yeah, yeah.
Linking between statistical and quantum in this way, or any relation exists in micro canonical or any ensemble?
Okay, relating, is it? Relating.
Yes, sir.
Hmm. So, it's slightly difficult question to answer straightforward. Okay. So, yeah. Yeah, so I don't have a straightforward answer for you right now. Probably I have to give a thinking on that. Yeah. Any other question?
The same participant had earlier one question. In terms of large system, we are using entropy for measuring other average observables, which is relating to quantum. Is it correct, sir?
Sir, repeat the statement again, sir. Let me.
In terms of large system, we are using entropy for measuring other average observables, which is related to quantum.
Yeah, yeah, yeah. No, up to certain extent only, because the moment you go for a larger and larger, so you can't use a macroscopic description at microscopic level. Okay. So microscopic means single individual qubit level or something. Several qubits together becomes reasonably microscopic still. But if you're talking about a very large number of systems, microscopic systems put together, then it becomes a macroscopic. There, the statistical physics may be correct, okay, but we can't draw the same quantum mechanical conclusions from there. There is something called locality, non-local and non-local effects and local effects. So those things will come into the picture. Okay, so it's not that simple. Yeah,
I think, sir, your system is working again.
yeah. I can see. I can see. In terms of large system, we are using entropy for measuring other average observables, which is relating to quantum. Is it correct? Yeah, that's what my answer, whatever I just said. Okay. Yeah, any other questions? No. Yeah, let me come back to this question again. Try to see. Now I can read. Linking
Sir,
between.
there is one more question here. I think that did not come over there. Can I read, sir?
Yeah, okay. Just read the question. I'll just go to that question. Yeah, read
Uh,
it.
Coherence. It's regarding coherence, sir. It is next. It came around 520.
520. Let me see that question. Okay, I can only go through up to 517. I don't know why.
Yes. I don't know. Maybe it is not getting updated. Uh, Coherence and decoherence depends on the energy of the system. If calculate the minimum energy of the system by calculating the partial function, is it possible to design error-free quantum computer?
Yeah, error, like, yeah, now you see, like, coherence and decoherence is there. No, let's say. Let's divide this entire thing into parts, this question into parts. Okay. So that is how we will try to analyze. Okay. So now, the moment you are talking about coherence, means many qubits are there. Okay. Let me call Q1, Q2, Q3, Q4, Q5, Q6, Q7, Q8, Q9. Okay. They may be interconnected. That is what you see in IBM network, the qubit architecture. Okay. Now I presume them to behave here in one way so that I can do the computing. Okay. But by interaction with the surrounding or internal interaction, they may go out of sync, incoherence with each other. It will become a decoherence. Okay, decoher. So decoherence may start happening at individual atom itself. What is that? Okay. So if I have electron in the ground state, individual atom or a qubit I'm talking about, if I send a pulse of pi by 2, it puts the electron in the superposition, does the Rabi oscillations. It's called Rabi oscillations. Okay. It's like it electron is exist at the one state and also ground state with the corresponding probabilities. Okay. Now the coherence is ensured depending on how much time the electron exists at the excited state, t1 time, which is 1 microsecond. Okay. And the oscillations would exist for certain time depending on the pulse. Oscillations will not exist forever. After some time, what happens? Oscillations will die down. How much time these oscillations exist? That is called T2 time. So T1 and T2 are very, very crucial factors, which will be some fixed values. If the T1, T2 values are fixed for every qubit, is fine. If the T1, T2 values of particular qubit is less than what is the actual case, actual requirement, in that case, what happens? This particular qubit goes out of the order, out of the sync with the other qubits. So that is what we call as a decoherence. I intend to do some kind of a quantum operation between Q5 and Q6. Let's say Q5 goes out of order, then my calculation is going to give us a wrong conclusion and errors would happen. Errors would creep in because of decoherence of qubit 5. Okay. Now, the way these qubits are rearranged internally with internal particular energy or a magnetic moment or all those things is discussed by or described by the accessible states of omega. Knowing the omega, you can calculate the probability distribution of this entire system. Okay. Now your question is here, you are saying, knowing the distribution of the system, okay, right? Let's say the decoherence happens at a Q5 or a Q4 or a Q2, we don't know. Knowing the distribution of the system, can we figure it out exactly where the decoherence can happen? Can we figure it out? There is a way to do a error correction. That is what your question I mean. So from the partition function from the distribution or a partition function, there is a way to find out, okay, where the probable error difference can start.
Sir,
Okay.
I think your screen is not visible, maybe.
Oh, okay. My screen. I'm sorry. I just share. What about now?
Yes, sir. Now it's visible.
Okay, so I'll repeat once again. Okay, so let's say I'll take an architecture of 9 qubits connected together. Okay, this is how IBM actually gives the architecture of their qubits on their computer back then. Now I think it's a 127 qubit system is only. I think we can still see other systems are qubit architecture. Okay, right? So here, if you just see, you can hear me. I guess one of the system got hanged.
Yes, sir. Yes, sir. Clearly.
Okay. So now decoherence means what for me? First of all, let me understand. Among this, all the qubits together, the decoherence can even happen at a very single atom itself. Okay. What is that single atom? If I have an atom which is in superposition of 0 and 1, means I have taken a system in a ground state initially. Okay, I've taken system in a ground state initially, electron. I just supplied a pi by 2 pulse to make the electron to do oscillation, that Rabi oscillation, which is actually a superposition state. Okay, now whether I will have a beautiful and required superposition state or not is dictated by two numbers, time numbers. One is the lifetime of the electron can exist, the average lifetime in the excited state. Another one is how long this oscillations of going back and forth exist. That is a T2 time. So that T1, T2 time is prescribed values. If the any by any means any of the qubit going to have a low T1, low T2, it is going to go out of order or without any sync with other qubits. Okay. Now I have a collection of qubits like this. How they could be arranged, in what energy they could be arranged, okay, in what accessible states they can be, is actually described by probability distribution function PR. Okay. Now, luckily for me, if by some means, if I am able to find out exactly which qubit, which location of the qubit, it is going to be abnormal. If I'm able to find, yes, of course, I can find a error correction for that. How? Probably, let's say Q5 is a problematic one if I am able to figure it out. What I'll do, I'll just do a swap between Q5 and Q8 and keep the Q8 at that point. Do the operation, whatever operation required to be done between Q mid one to the last one. Okay, I'll extract the essence and then re-swap again back to Q5 to Q8. Okay, so that may be a error strategy we can come up with. Okay, so of course, this probability distribution and partition function may help us in locating the possible errors, possible error locations. Yeah, we can come up with a strategy of error corrections. Yeah.
Sir, if you can check your WhatsApp, I have sent the snapshot of the questions.
Yeah, let me see. Okay, so let's go from, yeah, coherence and decoherence I just answered. Okay. Okay, what is the role of cryogenics? The role of cryogenics is to put the system to a very lower temperature. I can write here. No, I can write here. Okay. So to put that system to a very low temperature so that there will be no disorderedness in the system. As for the fourth thermodynamics law, if I put the temperature to absolute zero, then the system is no more going to attain any disorderness. It will be stuck with some fixed orderness. Rearrangement can happen, don't worry. Rearrangement can happen, but orderness will remain. It is just like the classroom is nice, cool, and temperature. There are so many desks, okay, and if I allow the students to sit in a classroom, they can sit anywhere, they can get rearranged. But if I close the doors and raise the temperature, in that way, what happens? They go haphazardly and move around, and they may try to come out of that particular room. That is the role of temperature doing chaos inside the room. The same story, if I reduce the temperature to absolute zero, individually the systems may rearrange, but overall they have a orderliness in that. So the entropy is not going to increase. So that is what we are expecting from a quantum computing. We want to reduce the temperature to very, very lower millikelvin. That is what cryogenics mean in the case of quantum hardware. Okay. And the next question, coherence in terms of thermal, how the phase change. Okay. The phase change in the mean, I mean, everything's becoming decoherence means coherence to decoherence, that is a phase change. Here in this case, we are not talking in terms of phase changes. The phase change is a macroscopic entity. Let's say liquid becoming vapor or liquid becoming a solid by sublimation, by cooling. Okay, right? So here in this case, I think the phase change from coherence to decoherence we can think, but not more than that. Okay, I think there is a question by Priyaji. I think I have asked. I don't know which question is that. Just check. Majumdar sir, please check our previous question. Okay, there is a question by Tripathi ji.
Sir, that
How
one
pure?
I already asked earlier. The
Ah,
previous
okay,
one
great.
I already asked.
Okay. How pure states and mixed states using the density matrix formalism used in quantum error correction. Okay, right. I don't know whether I have discussed it or not, but I can discuss it again. I hope you can see my screen now. I'm writing now.
Yes, sir.
Ah. Let's say I take a collection of qubits. Okay. For simplicity, I take only 9 qubits. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. Now, if I see now, all of them are alike in coherence. I'll represent them by one simple single equation as superposition state. Okay. Now, the ones which at the boundary, they're interacting with the boundary. You see, right? So as they're interacting, probably they may slightly change. Let me call them as some quantum states psi prime, where alpha prime and beta prime. What I mean is, they're all supposed to exist in, let's say, 40% in the ground, 60% in the excited state. That is what they're meant to have. The alphas and betas are meant to have, or alpha square, beta square meant to have a connection to their probability amplitudes. Right? Okay, but because of the interaction with the surrounding or walls, probably they had become alpha prime, beta prime had become something like slightly deviated. What is the deviation? Instead of having ground 40, they have 41%, 59% excited. Okay, so there is a slight change by the way. Okay, so I have two systems, two groups of system. What is that? Group 1 is quantum system psi, group 2 is quantum system psi prime. Now I can't have a same single quantum state representation for this entire group. So I need to have some other way of describing. So this is for 9 qubits itself. This is a story. If I have so many qubits there are groups of qubits which behave like psi 1, psi 2, psi 3, psi 4, psi 5, and so on. So now here at a given, like if I just close my eyes, pick a qubit out of this group, what is the chance of one of them falling into a particular group is given by corresponding probability P1. Okay. So there is a P2 to fall within this, P3 to fall within this. It's like I have 10 red color balls, 10 blue color balls, 10 green color balls. Like say, there are all different, 7 different colors of balls are there in the basket. Now the question, they are all nicely mixed. Then if I ask you a question, what is the chance of whatever ball if I pick by closing my eyes, what is the chance of it is falling into particular color? So then you say, let's say the red color ball, if I want to pick, there is a 10 red color balls are there. Out of 70 different color, 70 overall balls, the probability is 1 by 7. So likewise, I will have individual probability for particular group P1, P2 and P3. Now the question is, now the system is not pure at all. It's a mixed, very much mixed. If I have a divisions of individual colored balls in particular box, I can pick that color. Or let's say all the balls are of same color. That is a pure system. Okay, individually pure if all are in sight. But here all are in various possible size. So mixed system. So now to represent a mixed system, is there a short way of representing it? Of course, there is a short way of doing it. So they bring a method called a density matrix. What is this density matrix? Is they create a matrix row out of a quantum system by taking outer product. So you see, alpha ket is alpha beta, psi bray is alpha star beta star, which is alpha absolute square, alpha beta star, beta alpha star, beta absolute square. This is a matrix. What is this matrix is telling you? The off diagonal elements telling the energy, sorry, probabilities. Off diagonals are telling whether the polarization is existing or not. What is the polarization? Oscillations are existing between ground or not is expressed by these cross terms. Okay. So now the density matrix for pure system is like this. But I have a mixed system. In that case, how do I write a density matrix? So overall density matrix of a mixed system is the density matrix corresponding to a pure system with a probability P1, density matrix of second group corresponding to with the probability P2, and so on. Let's say there are n groups, each corresponding to probability amplitude, probability Pn, and this is the overall density matrix. Now, the overall density matrix, if you square, it is not going to be equal to the individual density matrix. But if you square a pure system, this is mixed, pure. If you square it, you will get rho, right? And the trace of rho square is actually 1. But trace of rho t square is not equal to 1, which is anything other than 1. In that way, you can find that the system is mixed or density, like a pure. Okay. So coming back to your question, what was the question? Can you, okay, let me see the question. How pure states and mixed states using density matrix formalism you used in quantum error correction. Okay. So in the quantum error correction, okay, we will ask where exactly the error is occurring. Okay, whether error is occurring at a first qubit or a second qubit or a third qubit, accordingly we are going to come up with the error diagnosis and error correction. Okay, so let's say I have 3 registers going. Let's say Q0, Q1, Q2. I have a problem with the Q1. Means it is supposed to be a 0 ket. It is becoming 1 ket. Okay. Or it's supposed to be a psi state. It is becoming psi prime. What is that psi prime here? Okay. 0 becoming 1 means the bit flip I am talking about. Bit flip. Okay. So this is alpha 0 plus beta 1, which becomes alpha 1 plus beta 0. Okay. So this is actually a X gate being acted like a error is acting like a X gate. Okay. Now all the qubits are in the supposed to be in same superposition, but the mid one is going a bit flip. Okay, in that case, how do I am going to do a error correction? I'm going to do a error correction by reacting x gate on psi prime. Okay, reacting x gate on psi prime to get back my psi. So that is how error correction is. Okay, so probably using density matrix we will not do it at this point. We are talking in terms of individual qubits, individual collection of qubits. Okay, several qubits, not too many at the level of density. So that's why the error correction as of now you can treat it as uh, acting. See, for example, here two qubits are fine. The mid qubit is problematic. What I'll do, I'll create a a gate sequence which has like this, nothing on the qubit 1. Okay, reversing, flipping on qubit middle, and nothing is on the last one, identity. So this is what the error correction is done in the case of 3 qubits. So at the density matrix level, probably you need to come up with the dense of qubits, sorry, qubit gates required to act on collection of various qubits. Okay, right. So how pure and mixed states using density matrix are used in an error correction? Yeah, that is what I meant. Okay, let me see next question. Is it possible we consider the local and non-local factors which are affecting microscopically statistical relation will lead to quantum observables can measure? Thank you for an explanation. Okay, yeah, so local and non-local factors. So local factors are fine, easy to address, we can understand. Non-local factors means then we will have to talk in terms of macroscopic. Okay, so macroscopic means no more quantum at all, right? Because we are talking in terms of large entities. So non-local factors means somewhere coming from very far. So in that case, we will be talking about a collection of microscopic systems. Okay. So, yeah, is it possible? Of course, not possible as far as my knowledge goes. Okay, and fourth law I have answered. What is fourth law? Please tell me the preferred textbook for QT02. Yeah, thank you very much. Okay, QT02 for a quantum sensing, I have few books. Okay, what I will do, I can share you those books. Okay, so this is a book. There's a book by Patria, Statistical Mechanics. That is what I am referring. And there is a Statistical Physics by Reef. Okay, this book you can refer. Okay, so somebody having any problem with understanding my lecture notes, I'll be sharing this book, which is available on the net, by the way, and you can refer to that. Okay, yeah. Let me go. Okay, it'll 68, 680 pages. So it will take some time. This is a very good book for QT02. Not QT02 for statistical physics, I'm sorry. For a QT02, uh, depending on the topic, we have to refer. Okay, let me see. Wherever there is quantum computing, you use Nielsen and Chuang book. Okay, and wherever there is a quantum mechanics, you can use there is a quantum mechanics by Shankar, a book by Shankar. So that can be used. Okay, quantum cryptography and all. Again, Nielsen and Chuang is beautiful book, is enough. Even the complexity classes also will be discussed. Okay, so wherever there is a Fermi Dirac distribution, whatever topic I am covering from statistical physics, that is from Reef or Patria book. Yeah, fine. So that is the answers from my side. Anything else, sir? Nothing, I guess.
No, sir. I think all the questions are tackled till now, and
Yeah.
yeah, we are over and above 20 minutes of our scheduled time. I think I can see the dedication of the participants. Also, they are highly into your topic, and they are asking so many questions.
Ah, right. Okay. Thank you. Thank you.
So, thank you, sir. Thank you for such a engaging session that the participants are really engaging. So, I think tomorrow we'll have the third session in this continuation, right, sir? So,
Yeah.
again,
If there is any, yeah, yeah, yeah. Continue, sir.
Right, sir. So, yeah, participants, tomorrow again the timing will be 3 p.m. only. The 3:30 shift was for today only. So please come at in time before we start the session so that you understand today also that if you miss some of the parts, it will be hard to understand the next part also. So please come by 3 p.m. tomorrow. And also, again, thank you once again, sir, for your time. And we'll again once meet tomorrow. And
Yeah.
then Monday we'll have another one. So
Yes, sir.
thank you, sir. Thank you once again.
Thank you,
We'll
Nanda, sir.
see
Bye bye.
3 p.m.
Yeah.
tomorrow. Thank you, sir.
See you. See you, all the participants. Bye.
Bye, sir. Diksha and Nitya kindly close the recording and all.